too cold out here right today, so you may see me again with the cap. So good afternoon and welcome back to the session for Graph Neural Network. We'll continue from where we have left. We'll quickly finish the content, okay, for the residual content, and then we immediately will move to next module, which is on the concept of the deep generative model. Okay. So let me quickly finish the content, hardly 30 slides. Okay. So most probably within half an hour, we'll be able to finish it because this is just a theory. And then we'll quickly move to the next one. But to set the context, what we were doing, we were primarily, we have explained the concept of classification activity related to the graph using neural network. Okay. So obviously the classification activity with the graph can be of will be of three different categories: node classification, graph classification, and then the edge classification. Okay, or edge prediction or link prediction. So link prediction can also be called as the um, recommendation analysis or recommendation prediction. So let us start again from where we have left. So this is the last slide where we covered in the last session. Now let's start with some work related to the link prediction, which have been done by the various researchers. So there was a paper with the name Link Prediction Based on Graph Neural Network, a heuristic method. Okay, a heuristic means a proper, because heuristic is again a word which has been widely used by the researchers. So heuristic is something where we start with some initial values, and then slowly and steadily, iteratively, this is an iterative process. So iteratively, we will be updating the values based on the neighborhood values, based on the based on some operation with a slight step further, with a step ahead. Okay, and then among all the solutions, we pick the best found so far. So that process is called as heuristics. So so the researcher Zheng, most of them are Chinese only. Most of the work that is being done by the graph neural network or deep learning on a graph is being done by um, either Chinese in China or Chinese outside world. And that too, I think we 5 to 6 years back. So the work that we are referring to are a part of their PhD work. So most of them has finished their PhDs on this area, and we are still covering those topic as a course. So slightly, to be very frank, they are a bit ahead of us in this area. The pen is, yeah, here it is. So what does he do? So he explores how to predict a potential or a missing edge between the nodes in a network using graph neural network. Are the key finding of this paper: limitations of the traditional heuristics. So traditional link prediction method, common neighbors, Jagged similarity, cursed index, relies on a predefined heuristics. We will have to search for the best solution in the neighborhood, and then we'll choose the best solution found so far. So while effective in certain cases, these methods are based on strong assumption that often fail, that often fail in a network like protein-protein interaction. So in a protein-protein, or we can say when we talk about biological data, this heuristics in information may fail. So they come up, so subgraph approach, subgraph based approach. So the author proposed a more flexible approach by learning from the local subgraph. The core idea was, instead of predefined heuristics, Model should learn a heuristic from data by extracting local information, local subgraphs around that potential link. So this allows the link to be automatically learned the relevant structures pattern from the neighborhood. So the heuristics belongs to the more generic class names graph structure features. Graph structure features are those features which are located inside the observed node and the edge structure of the network, which can be regulated directly from the graph. So suppose if we are focusing on this subgraph part. So how many subgraphs? So this may be one subgraph which have been extracted out. This may be the another subgraph which can be extracted out, and based on that they can predict whether there should be an edge between some labeled node or not. So this heuristic can view as a predefined graph structure features. A natural idea is to automatically learn such features from the neighborhood itself, just by looking at the neighborhood along with in the subgraphs. So the enclosing subgraph for a node pairs X and Y is a subgraph induced from the network by the union of X and Y's neighborhood, okay, are up to certain hop. Okay, so direct neighbors X and the collection of their X and Y, one hop neighbor. So if it is one hop, so direct neighbors of X and Y. If it is two hop, then neighbors of our neighbors of X and Y, and so on. So in this case, if my subgraph, the node on which I'm working on are A, B, and C, D, and the neighborhood size is I call, if I use it as one hop neighborhood. So if this is A, who all are the one hop neighbors? These are the one hop neighbors of A, okay, as well as when I'm talking about B. So who all are the one hop neighbors of B? They, this, and this. Okay, so these one hop neighbors are taken as one subgraph. Whereas if I'm talking about C and D, so who all are the one hop neighbors of C? One hop neighbors of C are these, this node, and this node. Whereas who all are the one hop neighbors of D? The one hop neighbors of D are this and this. So one hop neighbors are being included, and these are the enclosing subgraph, extracted enclosing subgraph on which we are working on. Okay, so this is the subgraph which we should work on, and this is the another subgraph based on the node of interest. Okay, if that would have been two hop neighborhood, okay, then two hop neighborhood would have been a slightly bigger. It include this node also. Okay, then these two nodes also. Okay, and this node as well, and this node as well. Okay, so in that case, if my criteria is two hop neighborhood, the subgraph on which I should work on will be this two hop neighbors, two hop neighborhood. Okay, similarly for this one also, some new nodes will be added. So like this one, and one more. Fine, I think. Okay, so in this case, if that would have been two hop neighborhood, my subgraph would be a slightly bigger one. Okay, not necessarily slightly, it can be big enough. Okay, luckily in this case, those two nodes was close together. So there were many overlapping nodes, but if there would have been some different, some non-overlap. If they wouldn't have been not direct neighbors or one hop neighbors or two hop neighbors, then in that case, the size of the subgraph can be even bigger. Now, what is the problem with the size of the neighborhood? I think in the last name, not in the last to last session, I was explaining you regarding one scenario which we encountered about the protein interaction for the cancer cell detection when we were talking about the hop neighborhood. So the moment it was one hop, it was around a few millions of nodes. Okay, not million, it was few thousands of node. But the moment when we increased one hop to two hop, it the size of the nodes in the neighborhood, the number of subgraphs becomes around a billion, which initially it was our program crashes. Okay, because of the memory issue, because we were using the sequential one, then we moved to the parallel GPU. Then I think it takes around 10 to 15 days to finish. No, one month to finish. Then we put some other restrictions. We change some values. I think Professor Vipin can explain you well. If you can ask them in the webinar, he can very well explain you because he was the only person working on that. So, so in that case, when we increase the neighborhood just by one hop to two hop, okay, there was a drastic, we can say, increase in the number of computations. Okay, so most of the time, to make the thing simple, it's better we should use one hop neighborhood only. So these enclosing subgraphs are very informative for the link prediction. All first order heuristics such as common neighbors can directly be calculated from the one hop enclosing of the subgraph. So direct neighbors, that's fine. Obviously, we are dealing with the direct neighbors. So it shows that higher order heuristics such as rooted page rank and curves often have better performance than first order, second order ones. Correct. But it has a limitations also. Not limitation, it has a it requires extra computation capabilities. But obviously, learning will be a bit more. To effectively learn good higher order features, it seems that we need a very large hop number h so that the enclosing subgraphs become the entire. Okay, I most probably it should be around in the few digits of no, not few digit, less than 10. I think based on the because we'll be dealing with the real graph, and the diameter of most of those real graphs are in between 10 only. Okay, so but for some cases we can have a large hop also, but most of the time it will be around 5, 6, 7, 8, not more than that. Frankly speaking, we have experimented till two hop only. I think two hop only, not more than that. So this result in unaffordable. This result in unaffordable time and the memory consumption for most of the practical network. So that's what we were talking about. So this was the problem with this. So we started with two hop and then somehow we end up with the one hop only. But do we really need such a large number of H2 or order the higher, sorry, I should read it. So, but do we really need such a large edge, the hop size, to learn higher order heuristics? Intuitively, we'll say that if I have a large hop size, I will have a bigger neighborhood. Fine. Some cases it is true. It will be a bigger neighborhood. But it may leads to one situation where if we keep a larger hop, in this case, suppose for example, so if there's a loop or something like this, okay, so when A and B are one hop neighbors as well as A and B are the two hop neighbors, A and B can also be a three hop neighbor where it is not in this case 1, 2, 3, 4, 5 hop, 1, 2, 3, 1, 2, 3, 4, 5. Okay, fine. So in that case, there will be um, in this case A and B are one hop neighbor, then two hop neighbor, then four, five hop neighbor. Okay, so ultimately there be repetitions. Okay, many number of nodes will be repeated if there is a cycle or something. Then theoretically it may be a good idea that okay, larger hop means larger neighborhood size, but it will add to our pressure of having unnecessary computation. Okay. So, but in that case, we can have a we can make our algorithm a bit intelligent about by using a concept of traversed so far and untraversed so far. Okay, so we can include only those neighbors which not have been traversed so far. Okay, all those nodes which have already been traversed means they're already a part of a smaller hop. So if they're already a part of a smaller hop, I think there is no idea. matlab, in some cases, it won't be a good idea to include them again for the bigger computation. Okay, but somehow we will have to make it. Then second, I think in the seal. So seal framework, they introduced the seal framework, subgraph embedding and attribute for the link prediction. This is what the name given, which uses GNN to learn link prediction heuristics. So seal extract the local subgraph around links, applies a double radius node labeling. They call it as DRNL technique to assign node labels and then train the GNN to predict a link existence, whether there should be a link or not. Now, this method enables a better learning for the graph structure features compared to the previous method that we have so far. Okay, but the thing is, it is still based on the structure, based on the hop. Okay, so the graph neuron with the common neighbors 3, Jacquard zero point 0.6, preferential attachment 16, curves 0.05, and so on. And they learn the graph structures. Based on that, they predict whether there should be a link or not. So the seal framework, for each target link, seal extract a local enclosing subgraph around it. Okay, what should be the local subgraph with one hop, ideally one hop or two hop, and uses a GNN to learn a general graph structure features for the link prediction. Note that the heuristic listed inside the box are just the illustration, and the learned feature may be completely different from the existing heuristic. So it's not necessary that they should be repeated. They can be totally different also. So this paper develops a alpha decaying heuristic theory, proving that many higher order link prediction heuristics can be effectively approximated using small local neighborhood. Okay, this was an important finding. So this reduces the computational complexity and shows that GNN can learn to predict link without needing the global information from the entire graph. Even with the local one hop or two hop, we may still get a good result. Okay, so that's why it says that alpha decaying, sorry, not alpha, gamma decaying heuristic theory. You increase the op, it will have a side effect. So experiment shows that seal outperform the traditional heuristics, latent feature method and state of arc link prediction method. So that means for them, seal works well. It is consistently achieving a high accuracy across various dataset, demonstrating that learning from a local subgraph is more effective than using the predictive heuristics. So this was an important finding from them. In seal, the hop number H is an important hyperparameter. What should be the size of the neighborhood that you have to work on? So this paper presents a novel GNN-based approach for link prediction, showing that learning from a local subgraph leads a better performance than relying a traditional heuristic method. You can do that. Okay, so this was an important finding. Then we come up across a different paper with the name Revisiting Graph Neural Network for Link Prediction, published in 2020. Okay, the earlier one was 2018 paper. Then we move a bit higher, not higher, up a bit ahead, and search for this paper. So the key finding for this paper was GAE, graph autoencoders method, which aggregate the node embedding to predict the links, are found to be less effective in capturing the structural information about the link. Whereas the seal, which focuses on extracting the subgraphs and labeling nodes based on their distance to the target link, significantly outperforms GAE method. So still in that case, we can say that, okay, seal was performing a better. It achieves up to 195% performance improvement on a large scale link prediction task. So there they come up and find out that, oh, seal is still better in some areas. So the paper highlighted that graph autoencoder method, which aggregate the node embedding, fails to capture the structural link representation. By contrast, seal uses the trick that assign the unique label to the nodes based on their positive relative target, and this enables the GNN to learn more expressive link representation. Okay, so seal till 2020 was comparatively better than the another. So seal method achieved the state of art performance on 3 out of 4 large scale open benchmark database, which they have mentioned into that paper. So this demonstrate the advantage of learning structural link representation over traditional node based method. Okay, but this was their finding. If you change the data set, and if your requirement might be even with a slightly different from them, then okay, fine. Then the result may be slightly different. Now, before moving ahead, I just one thing clicks into my mind. Um, okay, do we have mid-sem keys for the mid-sem exam? I do have the answer key. But I think as per the new norms, answer key need not to be shared. Okay, I will check with the authorities if I can still share the answer key, or if you came across any statement which is made by the program coordinator or any of the higher authority that the answer key will be provided to you, you can send a snapshot of that in instruction to me. Okay. Huh. I changed this screen to tomorrow is the last time for the evaluation. But I don't think 2024 all acha, if they have been shared, then I will check if I can share also. Because I think I was under the impression that this activity has been stopped. Okay. I think I have because the rules are being changed every time. So I think I was under the impression that I have came across a statement in which it was mentioned that okay, now onward we should not be sharing the answer key. It was a clear cut instruction. Somewhere I have heard, somewhere I have read. So that's why I have not shared it. But okay, I'll check with the authorities. And if yes, then most probably today itself I can share the answer key. I changed the screen for one request. Um, we are working on a particular subgraph identification problem only for a biological graph, where we want your support if you came across any small database, okay, a small data set, not the database. Do you have any idea of any of the small data set, preferably for biological or chemical data, with the ground truth, with the actual output? Okay, so wherever the ground truth is available, so that we can check and compare our own algorithm. So if you came across any small data set, not a bigger one, Okay, even the small data set will work for us, with which preferably the chemical and biological. Okay, if not, we can also work for the network or the social media graph. But the main concern is we are working on a subgraph identification. So where we have small subgraphs with the ground truth. If you came across, or if you have any idea, or if you know, is there any data set, then please share that link with me. Okay, because we are working on some GNN problem which need to be solved. Okay, got it. You got the question, matlab, you got the requirement. Subgraph means the labeling part. Ultimately, we'll be talking about classification activity only. So small data set with the ground truth means uh, meant for the supervised learning, but we'll be using it for something else to check the validity of our own algorithm, but a smaller data set, not a bigger one, because still it is taking around 10 to 15 days. Okay, any idea? Sorry, and any query?
Sir, actually, I have a question.
G.
Uh, you mentioned that seal is better than GAE in the architecture that right now that you were saying. So basically, what I understood that because in seal we are able to extract the subgraph and we know something about the structure of the graph, right? So is that what makes the seal better than GAE?
In that case,
Uh,
but
so I mean,
that again, in that case, they uh, outperform the GAE by using seal.
so I mean, how GAE and seal are architecturally so different, or what exactly changes uh, that basically makes seal better in certain cases, or what can be some other cases where GAE can also outperform, or
Hmm.
can we like if like what I read here, like before in the beginning of the class you said that because we have to extract the subgraph. And if a structure is that the only problem which makes the seal outperform, then there can be also different methods like positional encoding or whatever different techniques to give more structural information so that it maybe GAE can also outperform in some cases.
Huh. Matlab, it can be. Uh, because now this area is a very complex area. The reason is you change the scenario just by a small, okay, or you change the graph, even a graph, okay, then the algorithm which was performing better to you in the earlier case might not work so well in the change scenario.
Yeah, that I understand. That will
Hmm.
always be there in all different architectures also, like based on the different parameters and how we basically structure and the data, it will behave differently. But my question is more related to like how what made seal perform so better like than GAE even in that given situation. And because we did not discuss that part, that what makes seal perform so significantly better, or is there any way that GAE could have been also made better in some different cases? Because I
I think
understood
when
that it is only because of the structural non-awareness in the GAE, like where you were mentioning about subgraph,
uh,
or maybe a higher dimension of subgraph extraction.
mm, then I think we need to check. Oh, I need to have so in a Google Scholar. He'll give me. Oh, they have come up with the Seal Plus also. What was the original paper of the Seal? I think, was it this? Nine. This is 19. I need to answer your question. I think I need to go through the base paper to identify how what exactly supports him.
Okay, sir.
So he himself in this 2018 he proposed the Seal framework. So link prediction based on graph neural network. But where the paper is, yeah, here it is. So if you want a specific answer, okay, what was the reason why Seal was performing better, then I think I have read this paper. Just by looking at the structure, it somehow I have read this paper. But where are the notes? Okay, so I think what I'll do is I'll download this paper on the desktop. Okay, and then we'll answer your question because I have prepared notes for this. Just by looking at the printout, or we can say the face of that paper, it clicks in my mind that I have read this. And you can also do that. I will upload this paper in the portal also. Too much of mathematics, but huh. Okay, I'll prepare a summary and we'll share it with you because यहाँ देखकर लगा कि मैंने पेपर पढ़ा है. So is it okay?
Yes, sir. Yes.
Okay. Oh, so GAE predict linked using node embedding. Seal predict linked using the full structure context around the link. Yes, correct. A summarized answer for one. But shouldn't it make outcome uniform always, not just a specific scenario? Okay. So to Ashutosh and Bhupend, to answer all your questions, I need to go through that paper. So after that only I'll be able to answer, okay, what was the specific reason. But I think we have included few slides on the seal when we were talking about link prediction. No, this is a paper for, no, this is a module for the link prediction, so it should be there only. ठीक है. So I'll come back. कि what was the specific reason? So I should write it. हाँ, यही तो पेपर था. So what was the specific reason for being so good in link prediction? कि it outperforms GA. Open question now. You can also search for it. also. No, I should write this. This is not a part of this question. Hmm. Okay, I'll come back. I'll go through the paper and then I'll answer the question, because they come up with the even with the percentage also 195, matlab around double. So in that paper they might have specifically mentioned why should also be mentioned. I think. Oh, but this is a
Yeah,
different one.
absolutely.
Huh. But this is a different one. Revisiting graph neural network for link prediction. Oh, but the same author. You can just have a look. The same author. So they updates their strategy. So I'll read 2018 as well as 2020 paper, both. This demonstrate the advantage of learning the structural information over the traditional node based. Okay, fine. But they identify some challenges for the seal network also whenever we are dealing with the dense graph. So seal does not perform well on a dense graph like the data set which is given, where free parameter node embedding in GAE method shows better result. So this was the area when where GAE was performing better as comparison to seal. So this suggests the limitation in structural representation learning in a dense network. If my network is dense, but what limitations they have not disclosed. What problem was created? So which the paper identify as a topic for the future research. So okay, fine. So they identify, no, but they might have identified the limitations in which they promise to work for the future. So in conclusion, the paper emphasizes the importance of a learning structural representation for effective link prediction, effective uh, and establishes seal as a superior method as comparison to GA. Then there was one more paper, more recent one, last year, evaluating graph neural network for link prediction, current pitfalls and new benchmarking. Okay, and unfortunately, this again was Lee, GNN et al. Means most of them was Chinese only. So they addresses a challenge and the improvement in evaluating GNN model for the link prediction. And what was their key finding was, what was the pitfall in the current evaluation? Underperformance of the model due to the poor hyperparameter tuning. So properly tuned model, Neo GNN, outperform previously reported results. Okay, so they come up with a new GNN. They call it as Neo GNN. Lack of unified evaluation metrics and data split, so make it difficult to compare the method effectively. Different graphs have a different evaluation mechanism. Third, unrealistic evaluation setting. Using simple negative samples make the task too easy, misrepresenting the real world in performance. Okay? So the author proposed a new evaluation. They call it as heuristic related sampling technique, HERT. Okay. So related sampling technique. Okay. They call it as HERT, which generate hard negative samplings using multi-heuristic, provide a more challenging realistic. So HERT improves the evaluation consistency, offering the insight from a real-world application method. So in the fair and properly tuned condition, but they intelligently doesn't say how to tune it. Okay, but they said okay, we have tuned it. So and under fair and properly tuned conditions, some models show better result than the previous one. How and why they did not explain. A heuristic method can outperform the complex GNN based method under more challenging settings like hard. So they praises their model. So simple model perform better than expected under the hard, where advanced model that excels in easier setting faced a greater challenge. So their model exhibits a lower performance but reduced variance in a more realistic evaluation, making comparison more reliable. So the paper underscores the need of the improved evaluation strategies and suggests that the field can advance by adopting more rigorous real-world benchmarking problems, so that you can prove your own result. Then there was one more paper, page link, path-based graph neural network explanation for heterogeneous link prediction. Okay, so they proposes a new method, Zheng and all, and they name it as page link for generating the explanations in heterogeneous link prediction task. Till now, most of them were working for the homogeneous part, the homogeneous graph. They started with the heterogeneous graphs. So heterogeneous link prediction task. So it focuses on providing the interpretable, scalable, and heterogeneity aware explanation. And what was their finding? Their finding was connection interpretability, means whatever the connection is, you can interpret them. So the page link generate the explanation in the form of path between node pairs, improving the interpretability. Okay. So unlike this subgraph based method, path provide a clear connection between the source and the target, which was easier for the humans to understand. But the second advantage was whenever they were using the subgraph, they were talking about all the neighbors, sideold neighbors of a target node. In this, both the source and target, but in this, in spite of targeting, in spite of working on all the neighbors, they specifically work for the path between the source and the target one. And remember, in GNN, whenever I'm talking about path, or whenever anyone is talking about the path between source and the destination, definitely they are talking about the shortest path. Okay, so the shortest path is hidden. They can be multiple, but among them, the path, if any of the researcher uses path keyword in the graph neural network, that path means by default they are talking about the shortest path. Okay, if it is an unweighted graph, then the shortest path will be based on the number of edges. If that would have been a weighted graph, then the shortest path would be on the basis of the sum of all the weighted edges. Okay, in that case, when my graph is weighted, number of edges doesn't play any role. So by focusing on the path instead of subgraph, the page link reduces the complexity of the explanation generation. So that obviously, in spite of focusing on all the neighbors, all these neighborhood, we just focus on one path, one sequence of node from source to destination. So this method scales linearly with the number of graphs edges, making it efficient for a large scale. Okay, so even for a large scale graph, I'm not bothered about the neighborhood or the size of the neighborhood. I'm just bothered about the shortest path between that source and the destination, source and the target. So, and this page link was designed to work for a heterogeneous graphs where nodes and edges have a different types. So it leverages these types to generate more meaningful explanation, addressing the limitation in the previous explanation method that primarily work for the homogeneous work. So all the previous method, they works for the homogeneous one. So the method quantitatively improves the explanation of area under the curve. Okay, for the recommendation system on the heterogeneous citations. So user item graph with 9 to 35% compared to the baseline method. So they still, the performance was higher. And the human evaluation, page link was selected as a best explanation method in 78.79 of that time, and those numbers was given by him only. Okay, of that time, demonstrating its superiority in generating human interpretable explanation. Okay, so human can also interpret. So PageLink provides a robust framework for explaining GNN prediction in heterogeneous link prediction task, improving both scalability and the interpretability, while outperforming the existing method in quantitative and qualitative evaluation in both of them. So this finishes the uh, link prediction activity. 8:40 से 2:40. Okay, still we have around 1 hour 10 minutes. So quickly we'll move towards the next module, which we call it as deep generative model. Okay, but before that, any query? Do you need a break or should we continue? Usually in the past 11 session, I haven't, usually I didn't take a break, but if you still want, I can. Please confirm. Okay, okay. So let's have a 3 to 4 minutes breaks. So let's wait. Let's come back by 2:35. Okay. So I'll also have a glass of water. Oh, Shankar. So let's wait for a few seconds more. Uh, in the meanwhile, uh, acha, it is still recorded. So after the class, we'll can we have a short discussion about the flow of the course, because as we are moving towards the end, I doesn't want to make I doesn't want to spoil my end of the course. So any improvement, so we'll discuss at the end towards the last after the session end. Okay, anything else? Should we start? Should we start? Please confirm. Should I start? Please confirm.
கேக்குதுப்பா ஷேர் பண்ணு screen. கேக்குது
Okay.
ஸ்கிரீனை ஷேர் பண்ணு.
You were saying something about sharing of the screen. I have already shared it. Okay, take care. So thank you. Chalo. So let us switch a case now. So we'll be talking about generation, graph generation. So before that, the generative model means here we'll be talking about that the graph, or we can say the model should be able to generate the graph at random, which looks like real. Okay, so it's not generating the graph. Okay, so the artificially generating the graphs which looks like real. So this is not mine, this is our main criteria. Okay, we need to come up with a method where the model itself, we just give them a specification, we just give them some hint, and they generate the graph based on the criteria that we have given. So that type of activity comes under the deep generative model. Okay, it can have a wide area of application. One can be, suppose we have a model in which we just give them an input, okay, and some type of a graph, and then it generates the graph artificially. Okay, so we train him. Okay, we just an encoder decoder type of a thing. So we give them encoded graph, then they a smaller graph with a smaller dimensions, and from that they from that smaller information, or we can say latent space, they generate they regenerate they try to regenerate the original graph. Okay, so we have the original graph, the ground truth, and the generated graph. We compare them and we identify, okay, what is the problem, okay, where there's a mismatch. Fine. So in that case, by iterating this model, we can train him more efficiently. Okay, so the moment my decoder is encoder and decoder is trained, now I can remove the encoder. I can use only the decoder part. So I just give them a specific latent space. From that, my model should be capable enough for generating the real graph or anything artificially, okay, which looks like real or have all the properties which I have specified in my latent space. So this is the another perspective of deep generative model. Okay, so it's like training something. So it's like we can say a coach trained a player. Okay, so a coach is there by putting them in a various scenarios. The coach trained his player. Okay, when the player is trained enough, we can remove the coach. Now my player is capable of handling any type of situation. Okay, so that is the intention behind the deep generative model. Okay, but before that, we need to have a quick recap on the generation of a graph. We can say random generation. Okay. So the proper statement should be a quick recap of the random graph generation. How a graph is generated randomly. So traditionally, there are many models which can be used to generate the graph. We'll look at one by one and then quickly, and then we'll move towards the deep generative part. So what are the traditional graph generation approach? One of them is the Eridos Rhino model. Okay, or Eridos Rhini model. Sorry, not Rhino. Eridos Rhini model. The short form is ER model. Okay, so ER model means it gives me the probability. So the probability that a index in an adjacency matrix. So A is the adjacency matrix. U and V are the endpoint of an edges, or U and V can be the two nodes. Okay. So the probability that any two in any one index in the adjacency matrix, suppose for example this one, and suppose this is U, this is V. So U means suppose 7, and this means 5. Okay. So probability that A 7 comma 5, 7 comma 5 will be the index in the adjacency matrix. This will be 1.7. This and 5 is equals to 1 means if UV 75 is equals to 1, what does that mean? It means that U and V are connected to each other. So that means there is an edge between U and V. This may be the whole graph, whatever it be. Okay, in which U and V have an edge in between, they are directly connected, that will be equivalent to the probability R, which is user defined. So probability that two nodes have an edge is equals to R for all U and V that belongs to the vertex set. So that means this I will be doing it n cross n times. Means I will be checking this for each and every pair of U and V. Okay? Provided that U is not equals to V, means both the endpoints means no self loop. Okay, so this is the meaning behind this meaning. This sentence where U not equals to V means not both the endpoints of the edge are not the same node. Means no self loop. So this R will be some controlling density. Okay, so this R will be the probability between 0 to 1. So and more the probability means more the chances will be there that there should be an edge between those two pairs, those two pair of node. And if the probability is less, then my graph, the chances of two nodes being connected will be less. So how R is uh, controlling the density? More probability, more dance. Dance need dense. So R is more probability means more dense graph, less probability means sparse graph. Okay. So if R is more, graph will be dense. If R is less, graph will be sparse. Okay. One clarification I want. It's easy for me to say okay, R will decide the probability of the density of a graph. But how actually the probability will be implemented in this model? Can I think I've already explained you in my first or second session. Do you still remember how I should be able, how I can generate a random graph using this probability? How the probability is actually being implemented for the graph generation? Any idea? Okay. Um, before that, do you have any idea regarding the random generator, random graph? Sorry, value. Matlab, what to say? Random number generator. What is a random number generator and how actually it works? Because to implement a probability, I have to take I'll have to use the random number generator. So please confirm, do you have any idea regarding the graph, regarding the random number generator and the implementation of probability between for any activity? I'll take, matlab, if yes, then that's okay. If not, I'll take around 10 minutes to explain it. So please let me know whether should I move forward or should I explain that. Am I audible? Please confirm, am I audible? Is there anybody?
Yes, sir, you are audible. Yes, sir.
Acha. I was checking, is there anybody who is listening to me?
Everyone is listening, sir.
Okay. No, because sometimes it's become very boring. So it, matlab, for me, because I'll have to take a 2-hour session once. But for you, it is becoming slightly different because you'll have to take 8 hours. So you'll have to bear 4 persons like me.
Uh,
So it is difficult for you, not for me. It's hardly it will be because I used to have around 2 sessions on Saturday. So 2 hours in the morning from 8:30 to 10:30, and then 2 hours in the evening 1:30, 1:40 to 3:40, and then I'm free. So I'll have to speak for 2 hours. That's all. But for you, it is becoming very difficult because you'll have to listen to each and every person like us for 8 hours, and that too concentrate for full 2 hours. And a person like me who is like a who continuously speaks and doesn't demonstrate anything, so that makes the session boring. Okay, so how actually the random number is being implemented? So every programming language has a random number generator. Even Excel has a random number generator. Okay, so this rand function will give me a random number between 0 to 1. Okay, so I can generate a random number 0 to 1. Okay, this is a problem. Suppose you can just have a look my sequence. You can take a snapshot also. These are different these are different random numbers. Okay, but when I make a small change in one row, all of them changes. Okay, so that means they, if I have to regenerate the same random number, it is not that easy to me. Definitely they will change every time. So if I use the default random numbers, so then I cannot regenerate the same result. Okay, it's not the case that I can only generate a random number between 0 to 1. I can generate the random number between any range. Okay, so rand between top to bottom means 1 to, suppose, whatever the number is. Okay, so by this way I can generate a integer also between any range. Okay, and all the library functions provide this facility. Sorry, all the programming language provide this facility to generate the random numbers. Okay, but these are purely random. Suppose the number is 3671 for the first. When I make some changes, when I try to regenerate this number, I cannot regenerate, because if I use a default random number generator, I have no control over regenerating the same sequence. Now, why I want a regeneration of a same sequence? So suppose, for example, I am building a GNN model for something. Fine. And after 10 iteration, I encounter that my program crashes or my program gives a wrong output. Then in that case, how to track what is the problem? Either the problem can be with my code, or the problem can be even with the algorithm also. Okay, I have not even implemented correctly, or even my algorithm that I have used may not be correct. Okay, so how to identify what is the problem, or we can say we call it as root cause analysis, okay, which can be done only by debugging. So debugging means program slicing, in which you can generate, or you yourself might have done in Python, you print the value of the variable after certain iteration or a certain point. Okay, so that printing the set of value of all the variables you have used in your program iteratively will give you this program slice. Slice means what is the state, what is the value of each variable at a particular instant of time. Fine. Now, if your program terminates by keeping, suppose when your n reaches to suppose 10,000, your program terminates. So that means, and you are using some random variables into it. So that means the moment your value n reaches to I think 5,672, suppose for example, your program terminates always. Now, if I'll have to regenerate it, so what can I do? If I'm using a random number, I cannot generate the same sequence again. I cannot recreate the scene recreation, which the crime, the police and all used to do. They used to recreate the scene and then re-execute. Same is the case with the algorithm. Re-execution the algorithm one by one for debugging purpose to identify, okay, what might be the actual problem. So for that, it is advised to use pseudo random number. Okay, so you can you can search Google. You will find out some ready-made code available for pseudo random number generator that accepts one small input, which they call it as seed. Okay, pseudo random number accepts a seed, which means if you give them, and seed can be any a real number between 0 to 1. Okay, or seed can be anything. Seed can be integer number also. But the beauty will be if you give the same. So suppose you give the seed as 0.592472, seed 1. Okay, and some sequence is generated. Suppose this one. Okay, so this sequence is generated. Okay, at this point, so you generate some random numbers for doing your activity, and at this point your algorithm terminate. Okay, so this was the last value which might be creating a problem for you. So if you give the same seed again, the same set of sequence, same random numbers will generate again, and after certain iteration, this value will regenerate. And then at that moment, you can stop your program, or you can have the value of those variables, and you can identify what actually had happened to the program so that it has crashed. It has crashed. So this is the beauty of random numbers. Matlab, this is the use of random numbers, and this is the beauty of pseudo random number generator. Okay, so whenever you use as a programmer, as a model developer, wherever you are using any random number, it is advisable to use to write your own code for pseudo random number generator, so that you have a control over your code. Okay, fine. Now, so suppose you have a pseudo random number generator, and you generate the values, okay, at your own. Fine. Now, how can I use this probability? So this is my probabilities which I'll be generating, 1, 5, 7, 7, 6, 4, and so on. So how can I use this to build a graph? Okay. Now give me one probability. What should be the R? What should be the value of R which I should use to generate the graph? Give me one value of R. One probability. Give and any. You can use Bernoulli method for probability implementation. Yes, it is. Bernoulli means yes or no. So we will be using the Bernoulli method over here also. But the thing is, I'm trying to explain how the probability is being implemented into your code. Suppose if I say, give me a probability, give me a value of R which says that, okay, what should be the probability that there should be an edge between two nodes? I repeat again, what should be the probability that there should be an edge between two nodes of a graph? More the value, more the graph dense, more dense the graph will be, lesser the value, the sparse the graph will be. So give me one value of R. Any value and any random number between 0 to 1. Give me R. I request, or I can regenerate by myself. It will be good if you give me 0.894. Okay, correct. Okay, so what does this mean? This means that there are 89.4% chances that every two node have an edge. So I'm using a model, GNR model, where n is the number of nodes, r is the probability of edge between them. Okay, and suppose I want to build a graph of 20 nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I should write the numbers directly. It will be easy for you to understand. So I'm assuming that my graph I'm intentionally putting all those numbers randomly. Okay, so I need to generate a graph of 20 nodes. GNR model, where n is the number of nodes, r is the probability, and my r is 89.4. What does this mean? This means that probability that every two node, what is the probability that every two node will have a edge between them? Okay, and I'll be using the matrix, the probability 16, 17, 18, 19, 20. Correct. Now 1, 20. Fine. I can delete the rest. Okay. So I have generated a probability. And what is the size? 894. Where it is? 0.894. So I should reduce the 894. Okay, 3 to 3 decimal place. Correct. So this is my matrix. That, and what does it mean? That probability two and two क्यों होगा? 9. Oh, I made a mistake. While deleting it, I should not delete it. It should be 1 to 10. It should be 1 to 10. Now it is correct. 3. Fine. I should make it visible. I can delete rest. So this is my matrix probability that there should be an edge between them or not. Okay. So what is the probability that and I doesn't want a self loop. Okay. So U and V not equal. Fine. Okay. And I can focus only on the upper part because okay, let me draw a directed graph also. Okay. So what is the probability that 1 and 2 should have an edge? Okay. Now, when you say my probability is 894, what does it mean? It means that I have divided the scale of 0 to 1 into 2 part. This R. This will be my R, which is 0.894. Okay. And I say it is 1. So that means if it is in that range, it will be 1. If it is beyond that range, it will be 0. Okay. So it means that if the random number which I have generated is in the range of 0 to 0.894, means within that range. So in that case, I will have an edge between those two nodes. If it is from 894 to 1 outside that range, so that means I will not have it. I will not have any edge between them. Okay. So if it is 0 to 1 and this is 0.894, so that means 89.4% means this area covered. This area means 89.4% is covered by 1 and 0 have only a chance of 894 minus 1000, 1000 minus 894, it will be 6106, 206, sorry. 106 only. 0.106. Okay, means 89% chances हैं कि there will be an edge between every two pairs of a node, and 10% chances हैं कि the edge those two nodes doesn't have. Okay. Now let me generate the graph. So for node 1 and 2, 0.780. Yes. So first answer is yes. So that means 1 and 2 will have a edge. Then 1 and 3, 0.776. Yes. So that means 1 and 3 should also have an edge. Then 1 and 4, 3, 5, 1. Yes, again. So 1 and 4 will also have a edge. Where it is 4? Here it is. Okay. 0.869. Yes. So 1 to 5 will also have an edge. Okay. Suppose this value is 0.995, 994. Okay. Now 1 to 6 is 0.994. So 1 to 6.994 means the threshold value is 0.894. It is outside the bound. So that means 1 and 6 will not have a direct edge. So that means 1 and 6 will not be connected together. Okay. Similarly, suppose for example, if it is 987, okay, 988, again beyond that range. So that means 1 and 7 will not have an edge. So you can just have a look in that how many edges are there which are greater than, highlight the cell, greater than 0.894. Okay. Oh, sorry. I'll have to do it for all the graph. 0.894. Very few means they will not have an edge. Whereas less than 0.894 means 399999. I will mark it as green. Okay. So this means that if I intend to generate a graph, there will be only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Out of n into n minus 1 means 20 into 19. Only how many? It was, I think it was 36. Okay. So 36 missing link. Rest all the nodes will have a direct edge. Okay. So that means more probability, more my graph, more dense my graph is. Okay. If I reduce the probability, suppose if I keep P, the probability to be 0.734, whatever it be. Okay. Now, so if I'll modify the value. Okay. 0.7354. So how many edges will be there which are lesser than 0.754? I'll mark them as a green. Still more, but comparatively lesser than 0.954. Okay. If I further reduce the probability, lesser than 0.501, suppose for example. Then slightly lesser. So lesser my probability is, sparse my graph is. Okay. If I keep to be 0.3, then I will have slightly lesser number of nodes, lesser number of edges, but still my graph will be correct. So this will be my GNR model in which N is the number of node is fixed, R is the probability which is given to me by the user, and based on this probability, my random graph will be generated. Okay, now if I use a pseudo random number, then if I want to regenerate a particular graph, I can. I give the same seed, I will have the same sequence of numbers, and I can have, with the same probability, I can regenerate the random graph. But if that would have been a purely random number, then I would not be able to regenerate the whole value. Even with a small change, I have no control on the random numbers. Okay, those value will change. So this is how the random number, the random number and the probability comes into play while doing any activity. When I say, okay, 50%, the probability of doing this is 30%. So what I'll do, I'll generate a random number. If it is between 0 to 0.3, my answer will be yes. If it is between 0.3 to 1, my answer will be no. Clear? So this is how the probability and the random numbers come together and play for doing any activity. As a programmer, you should know. As a model builder, you should know how the probability is used in doing any of the activity. Whenever you say, okay, do this with certain probability. I hope that's clear. (36/380). अच्छा हाँ ठीक है, 380 कहाँ से आया? Thank you, Batendu. But Ravind, I need to clarify you. I need to clarify your doubt. You have posted something 360, 36/380. So 36, what is 36 and what is 380? Can you please reveal it? 19 into 20. Acha, 19 into 20, 380. And acha, 36 will be the missing edge. In the previous example, when I highlighted it, the 36 was the missing edge. Actually, I cannot regenerate that. Okay, ठीक है. So 36 out of 380 was the missing edge, and rest of them means 36 means 70, 64. So 264, no, 364 will be the edges in the graph. Okay, fine. So this was the GNN model in which we give them a number of nodes and the probability. Okay, so in this case, we just give them an R and this probability. So matrix of size n cross n will be generated with the probabilities. Okay, whoever is greater than that number will be 0. Whoever will be lesser than this number will be 1. And simply, straight away, we can generate the whole graph. So whole graph is generated straight away. So we'll start with the forest, number of nodes, and then we insert the edges one by one. So that means, but in this method, a whole graph is generated all at once, iteratively, but a forest is being, we started with the forest and then we ended with the graph. The next model of generating a random graph is GNN model. We give them the number of nodes and the number of edges in a graph. Okay, now, how does this model works? So suppose, for example, let me change the color. So in a GNM, we start with, suppose, 20 and 195. Okay, so I want a graph with the 20 nodes and 195 edges. How can I do that? So in that case, what can I do? I can generate, I'll have to generate 195 edges. Okay, so I will generate to both the endpoints 195 times. Okay, so I'll generate two random numbers between the range of 0 to 21. So what I'll do, I will generate 195, 195 edges. So how can I generate a 195 edges? I will generate 195 into 2. Okay, so 195 into 2 nodes, provided that u not equals to v. Okay, u not equals to v means both two endpoint should not be the same. I'll do it 295 times. Okay, so how can I do that? So just this is u, this is v. No, 295 नहीं कितना 195. Okay, so between 1 to 20. Okay, and same is the case. Uh-huh. 1 to 20. Oh, unfortunately, they both are same. If u equals to v, we'll say regenerate, or else I'm done. Okay, fine. So I will execute this 195 times, or I'll generate in enough set of numbers. Okay, and then so my first number is, what I'll do is C, and I will have a value. Oh, so this is my u and this is my v. Okay, so I'll generate two random numbers, and I should ensure that, okay, both should not be same. Okay, fine. So 8 and 8, discard. Next is 15 and 19. Yes. So I will add an edge between 15 to 19. So whatever my 15 is, wherever my 15 is, and wherever my 19 is, I'll generate an edge. Next is 10 and 9. So 10 and 9, I'll generate one edge. Then 4 and 13. So 4 and 13, I'll generate one edge. Then 17 and 13 and 7. So 13 and 7, wherever it is. Okay, so similarly, I will keep this process, I'll continue with this process 195 times. Okay, provided both the endpoint should be different and the edge should not be existing. Means it should not be the case that 13.7 is edge is already there. Okay, if it is directed, then that's okay. 13.7 is okay. And if some edge in 13, so in that case, it can be this also. So for undirected, if the endpoints are swept, means existing edge. So if it is undirected, we'll have to discard it. Okay, like a same node. This will discard. Okay, and same is the case here again. 19 and 15, 15 and 19 and 19 and 15 should be discarded if it is undirected. If it is directed, then 1519 can be accepted and 1915 can also be accepted, because 15 to 19 is a directed edge from 15 to 19, whereas 19 to 15 will a directed edge from 19 to 15. So in that case, if it is directed, it is accepted. But if it is undirected, we'll have to discard it and generate a next sequence of numbers. Okay, so this is how we'll generate a random graph using GNN model. We'll continue this process 195 times. Okay, with unique, means non-repeated nodes. Same node should not be generated, and we should generate a non-existing edge. Okay, so n is the number of nodes, m is the number of edges presented in a graph, and somehow we will end up with a graph with 20 and 195 edges. Is both the models clear? GNR model and GNM model clear? I hope these are the simplest one. These are the simplest one. So it is very easy to implement. No need to use any no need to use any brain. Simply a random number, generate a sequence, match whether it is within that range or not. Based on that range, assign 0 or 1. Simply. Time complexity will be the size of the graph. N cross M means N cross N. V cross V means based on the number of vertices. But it has a problem. Although I'm not specifically taking care of this one, connectedness of a graph need to be checked and ensured by the programmer. Okay, although I say that, okay, when my graph is dense, wherever it is, okay. Sorry, it was here. Okay, in that case, I was adding those edges, I was connecting those nodes randomly. I was not ensuring that a node, that the graph is connected or not. Most of the time, if I keep my probability high, then chances are more that my graph is connected. If my probability is less, then chances are more if my probability is high, the chances are less that my if my probability, this probability, either this R, or if this N and M means this proportion is high, so that means graph will be dense. If graph is dense, then probability of being a connected graph is more. If this probability is less, or this proportion N by M is less, then that means my graph will be sparse. If my graph is sparse, but in both the cases, it is not guaranteed the graph will be connected. Okay, it may be possible, because it is random graph, it may be possible that the node number 20 is left isolated, is not selected by anyone to be connected with himself. Although the probability is low, but it may be a chance. It may be the worst case. So the graph will be connected in both the scenario. Is it guaranteed? No. So we'll have to, if you're generating the graph at random, you'll have to ensure whether the graph is connected or not. How can that be checked? How can that be checked? While generating a graph, you can always keep a degree metric, or we can say a degree array of each node from 1 dash 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 to n. Okay, initially the value will be 0. Okay, the moment you are adding an edge, you can update that. So that will be equivalent to its degree. And if there is any 0 left, so that means that will be an isolated vertex. Any 0 will give me an isolated vertex. But again, there's a problem. I'll not be able to detect the connected component, disconnected component. How can that be checked? So this can also be checked in terms of matrices. Okay, even and that too from the eigenvectors also. Okay, so number of connected components. You remember, if you arrange the if you identify the eigenvalues and eigenvectors, okay, so from there you can identify how many connected components are there. So, but it has to be done by the programmer. It's not always guaranteed. So programmer has to take care. But and so this was a smaller problem. This is a bigger one. It does not generate the realistic graph. It generates a dense graph or artificial graph, but it will not be able to generate the realistic graph. What is the property of the realistic graph? A real graph? Power law, degree distribution. Okay, so does not capture the degree distribution, existence of communities, node clustering coefficients, occurrence of structural motifs, the power law, and all those things not be visible in this. Okay, not guaranteed. So although it is capable enough of generating or a graph with a certain probability. So suppose, for example, if you'll have to perform an experiment on a Facebook network, Facebook connectivity network. Okay, so until unless you knew those values of of the Facebook network, okay, you cannot say this this artificial graph is exactly a copy of a of that Facebook network. No, you will not be able to generate it. Okay, you'll try to mimic, but this Eridos-Rini model will not be able to give you exactly the same graph which you are looking for. Okay, for that we'll have those deep generative model which looks like real. Okay, so it does not capture the degree distribution, existence of communities, node clustering coefficient, occurrence of structural or the patterns into the graph, and so on, and dash dash dash. So we can generate a graph. So the next method was stochastic block models. Okay, this is again a method of generating a random graph, but it can include the, it can have a community property. It can have a community structure into the graph. Okay, because here it's easy to implement, but we cannot ensure the degree distribution, communities, and so on. Just simple graph. So if I want to have a community structure into a graph, how much time do I need? Half an hour more to complete? 10 minutes. Oh, my this watch is telling 3:13 and this is 3:20. Oh, 3:30. Oh, this is 20 minutes late. Okay, I thought in this watch it is 3:15. Fine. I'll try to cover whatever it is possible. So stochastic block model means, how does it implement? It asks how many communities you want. So number of blocks or community required are specified. Okay, so in this case, what is asked? What is the probability, or how many number of edges you want into the graph? In addition to it, the stochastic block model also want how many clusters you want. Suppose I say I want 10 clusters. Okay, so in that case, first thing is the input is how many block of community you require in that artificially generated graph. So how to do that? So every node U that belongs to the vertex set has a probability Pi belonging to that block or community. Okay, so that means Pi will be the probability that U belongs to that community, any arbitrary node belong to the ith community will be the PI for all the nodes of the graph, such that when you sum all the probabilities, sum of all the probabilities is equals to 1. What does this mean? This means that every node should have a probability pi. Means suppose if suppose you want gamma to be 7, okay, so you want gamma to 7, so that means along with every node, suppose A, okay, every node has a probability pi, means it has p1, p2, p3, p4, p5, p6, p7. Okay, every node has 7 different numbers, 7 different probabilities. Okay, so by this 10, suppose for example, this number comes out to be, I can have, suppose some different 7 different numbers, such that sum of all those PIs is equals to 1. So 0.7, 0.3, then 7 3 10, 0.20, 0.2, then 0.35 and 0.9 something. Okay, 1, 2, 3, 4, 5, and then 0.4, no, 0.32. Okay, let me check. 0.07 नहीं ज्यादा हो गया, 0.07, क्योंकि ये तो सब कुछ बराबर हो जाएगा. So 0.07, 03, 2, 3, 5, suppose some 7 different numbers, such that sum of 7 numbers, 1, 2, 3, 4, 5, 6, 7, 7 numbers is equals to 1. Okay, H6 to H12. So I come up with some probability 0.01, 0.08, 0.8, 9, 0.08. Zero 0.824, whatever it be, 0.3, 0.39, 0.157, or this will equals to 0.8047, 1 minus 0.1047, 1 minus 0.1047. Okay, so suppose this might be 7 probability values assigned okay, so this may be 7 different. So every node has a probability pi of belonging a block to the community I. Okay, and this is for all the nodes. So this is the matrix for node 1, p1 a, such that it should, what does the impact of probability equals to 1 means? It should be a part of any community, because I will have a random number 0 to 1. Okay, I will generate a random number, and it should belongs to any of this class. So community 1, community 2, community 3, community 4, community 5, community 6, community 7. So if that probability, and we'll have we can say what to say, um, uh, prefix sum. Okay, So if it is belongs to that category, that range, means it will be equals to this value plus the previous one, and this will be equals to this plus the previous one. Is it so? 0.1 half. So this will be, if it is 0, 0.02, 02.08, then community 1, 0.8 to 0.08 to 0.28, community 2, 0.28 to 0.438, community 3, 0.438 to 0.565, community 4, 565 to 6477, community 6, 6477 to 0.8047, community 6, and 0.8047 to 1, community 7. So this is how the probability, the community will be decided based on the random number generated for each node. So we'll be doing it for each node, and while doing it, we will decide which community it should belong. Okay, so every node will belong to any one community. So edge probabilities are then specified by a block-to-block probability matrix, which with Cij gives the probability for an edge occurrence between 0 to 1 of order gamma cross gamma between a node of n, that should be, and this is within community, and the another probability game will be across the community. Okay, so a connectivity that different communities are connected, block Ci to block Cj, okay, belongs to this community, but also have an edge to the another connectivity, also have an edge to the other community. Okay. So the generative process for the SBM model is as follows. How much time do I have? Okay, so I'll be able to finish this SBM and then quickly. So it will be, so for every node, we'll assign U to be block Ci for a sampling for a category distribution, whatever it be. And for every pair of node, whether they should be. So this will be a matrix. So alpha will be the probability that within the community, within the connectivity, within the this alpha will be the probability of connection within the within the community, probability of an edge within the community, and beta will be the probability across the connectivity, because we'll have to make the graph connected now. Even those communities may be connected even with the weaker connectivity, but those community by itself should also be connected. Probability of an edge across the communities, across the clusters. So alpha will be far more, means my communities has to be dense. So this probability will be high, will be very big as comparison to beta. So this will be the alpha will be the connectivity within the connectivity within the community, and beta will be the connectivity across the communities. So this is how we can implement. So just by doing it, what is the benefit? We can implement a community structure into it. So like, okay, so this will be the beneficial part, but it also have some limitations. The beneficial part is it include community behavior. Okay, but it fails to capture the structural characteristics, degree distribution, and so on. So individual most of the nodes that present in a real world graph. So all the nodes within the, and the second problem is, as this probability of alpha and beta is fixed, So all the nodes within the community will have the same degree distribution because alpha is fixed. So this means that structure of the individual community is relatively homogeneous in that all the nodes having similar structural property means all the nodes of a same clusters will have a similar degree distribution, or all the and they have the same clustering coefficient. Okay, and and this may have, but in a real graph, homogeneity is not being observed. So unfortunately, however, this homogeneity is quite unrealistic in a real graph. So this has a problem that all the communities will be homogeneous, which doesn't resembles the real-time scenario, because in a real-time scenarios, clusters or communities may have a different structures, may have their own different connectivity, may have their own different density. So in real world graph, we often see much more heterogeneous with varied degree distribution. So although we were able to implement a um, communities into the structure into the artificial graph, but unfortunately the structure was homogeneous. So the third method was preferential allotment, preferential attachment. Okay, the time has passed, so I'll stop over here. I'll finish the next module, the next slide in the next session. Okay, so in any clarification required, is it good? Okay, so I'm stopping the recording.